Because now it will become positive. When you take a mod for that, that's how the value will come. And in denominator we have NCP T2 minus T1. Well, you have reached the efficiency, but all these terms are unknown. We don't know. The temperatures are not known. Only thing known is pressure varies n-fold. So now can we find out what is the connection? Do we have any connection between T2 and T3?
Adiabatic, so we can T2 gamma.
Yes, T2 and T3, the adiabatic process. So can we say, what do we say?
T2 gamma minus.
No, if you use volume, the problem is we don't know volume there. We don't know relation between pressures. So use the temperature pressure relation, then you will be able to simplify. Otherwise you are introducing more unknowns. NP naught power 1 minus gamma T2 power gamma is equal to P naught power 1 minus gamma. Can we write this? So what does your T3 become? So your T3 becomes, we can write like that, N power 1 minus gamma by gamma times T2 is T3. Similarly, what is the relationship between T4 and T1? Rather, it's a similar relationship. Same logic we can use for T1 and T4. NP naught power 1 minus gamma times T1 power gamma is equal to P naught power 1 minus gamma T4 power gamma. So that implies T4 equals N power 1 minus gamma by gamma times T1. So substitute these values here and simplify to get your answer. So final answer. Yeah, so what is the efficiency you get?
1 minus gamma by gamma.
Yeah. So I'm writing the efficiency here itself. 1 minus N power 1 minus gamma by gamma. Is that okay? You can factorize T2 minus T1 by substituting it there and you get this result. Okay? Question 1. Efficiency of the cycle is, now the PV diagram is given and you have two isobaric and two isochoric processes. Yeah? So, look here. I can find, suppose I take this temperature as T naught. What is the temperature here? This will be 2 T naught. Temperature here is T naught. This will be 3 T naught because the pressure has increased 3 times. And here, what will be the temperature? This will be 6 T naught. Is that okay? We have found the temperatures at every point. Now can you not find QAB, QBC, QCD, etc.? Everything is in terms of T naught, and NCP delta T is for isobaric process and CV delta T is for isochoric process. It's a monoatomic gas. Just substitute and get your result. Can you not get it? Question 1. Is that fine or what? Yeah. Is this much hint fine? Do I have to explain further? Yeah, first one who asked? Yeah, is that okay with you?
Sir, I added up the heat for all the processes using NCP delta T, NCP delta T.
No, just a minute. Efficient. Did you check which one is positive, which one is negative?
Yes, sir.
So what is the problem? You didn't get the answer or what?
I got efficiency as 1.
How can you get efficiency as 1? Yeah, just cross-check it with some of your friends. Will be able to do it. I don't think any problem is there. Yeah, I'm going ahead. You check it out with one of your friends. Will be able to do it. See, third one. You have got. There is a cylinder, and you have a piston in the middle. The total length is 84 centimeters, so can I say this is 42 centimeter and 42 centimeter again? So what's happening here? The pressure is 27. Pressure is 1 atmosphere and temperature is 27 degrees centigrade on both sides. Okay. Now what happens is, if the gas on one of the part is slowly heated, Now piston will go to one side and we don't know how much it has gone. Let us say it has gone by X. It will be 42 plus X and this will be 42 minus X. Now finally they will again have the same pressure, that's why they are in equilibrium. And this temperature happens to be 57 degrees centigrade now. And the other one is maintained at the same temperature, 27 degrees centigrade. Now if you write down the PV by T graph, PV by T volume, number of moles will be same for both of these. What's the number of moles in this? P naught 42A, A is the cross-sectional area by T naught. We'll take T naught in terms of 300 Kelvin, okay? Is equal to, what is the new pressure? P, and that will be 42 plus X times A by 57 degrees centigrade is 330 Kelvin. Similarly, we can use for these two, if we use for those two, it will be P naught 42A by 300 is equal to P 42 minus X by A times 300. Divide the two and get your answer. You'll be able to solve it. What is X equal to? You'll be able to solve for X. So if you divide the two, what do you get? You get 42 plus X by 42 minus X is 330 by 300. So that's 11 by 10. So X equals 2 is self-evident. Yeah, is that fine? This equation divided by this equation gives you this is solution. So I move on to the fourth question. The fourth question, what is the process A and what is the process B? A is isochoric. A is isochoric, so delta U is the same as Q will be equal to NCV delta T. Okay, for A. And for B, what is given? For B, delta UB is supposedly 100 joules.
Compare it to delta CVDT and calculate DT.
Yeah, the same amount of heat is absorbed by A and B. So delta UB is NCV delta T and QB is NCP delta T. So what do you get QB as? QB will be CP by CV. What is CP by CV for monoatomic gas? That's 5 by 3. So Q equals this into 100 joules, that is given. So 500 by 3 joules. And delta QB happens to be QA and that happens to be delta UA. So that will also have the same answer. 500 by 3 joules. Is that okay? The eighth one. See what is given is the following internal energy and heat are given to you. Delta UAB is given. Delta UAB. See, you can find QAB. QAB is delta UAB plus WAB. Delta UAB is given to you as 400 joules. Do you know WAB? WAB is the area under the graph. So how much is that? 3 to the power 5 into 0.5. Okay, joule. How much is this? This is 1.5. Yeah, this is 400 kilojoule. And that's 400 kilojoule plus 150 kilojoule. Yeah, that's right. So that makes it 550 kilojoule. And also QBC is given. P equals minus 500 kilojoule. Now you see the QCA, see sigma Q cycle will be equal to sigma W cycle. What is the work done by the cycle? Work done by the cycle is the area under the graph. What is the area under the graph?
Half into 10 to the power.
Yeah, you can find the area of the triangle. Okay, I'm leaving it here. For the Q cycle, you know AB, you know BC plus QCA will be Q cycle. So you can find these out because you know the other two. and get your result. Yep, shall I leave it here? Ninth one is a polytropic process. PV power minus 2 is a constant, or we can say beta equals minus 2. For the polytropic process, what is the work done? So substitute and get your result. This is the ninth one. Work done in a polytropic process, we can say like this, and you get your answer. 10th one. 10th one, say your piston is moving with a constant speed. You have P naught. No, the atmospheric pressure is to be neglected. Okay, forget this. This is mg, and you will have the pressure of the gas. So we can see that it's a P equals mg by A. It's an isobaric process when the piston goes up. So if you use Q equals delta U plus W, also we are saying the temperature remains unchanged, so U is 0. The work done will be the force into, what is the work done by the gas? That will be equal to, what is the heat produced? Heat produced is I square RT as a function of time.
Can you please repeat it?
Yeah. The heat produced is in the resistance I square RT. What is the work done? The work done will be the pressure into change in volume. Change in volume will be Vt is the distance travelled and A will be the. So equate the two, you will get your answer. This is equal to what? What is PA equal to? It will be mg. Mg Vt is equal to I square RT. So you get your V from here. So you can find your V. The 12th question. 12th one.
So can you explain it again?
See, Q equals delta U plus W. It is given that the temperature in this process is constant. Temperature is unchanged, so the gas inside will be having an isothermal process, which means delta U is 0. Okay? Now, there is no change in internal energy of the gas, and this is increasing, it's moving with a constant speed. If it's moving with a constant speed, the pressure acting will be constantly there. P delta V will be the change in volume. If this moves with a distance V in time t, what is the volume created?
Vt.
That's what I've written here. Pressure happens to be, PA happens to be mg. So put it there. I square R is the power consumed by a resistance when a current I passes. I square RT is the heat produced. Equate these two to get your answer. That's all. Is that okay? 12th one. If the gases are compressed to an initial volume, that means you have a PV graph and from a funnel to the same funnel volume, one isothermally, one adiabatically. So if you compress it like this, you can see this is isothermal and this is adiabatic. So which one has a greater area under it? Which one has a greater? You can see isothermal pressure is more than adiabatic pressure.
Yes.
All right. In adiabatic, if volume becomes less, temperature will be more. Which will have a greater temperature, T1 or T2? This temperature is T1.
So adiabatic
Adiabatic is a steep.
I'm sorry. Yeah, that's right. The steeper one is adiabatic. Steeper one is adiabatic. Yes, this is it. So now you can analyze it. So area under the graph for adiabatic is more, so work done is more on the gas. And temperature you can see is for adiabatic temperature will be T1 will be greater than T2. Yeah, funnel pressure is greater. Everything is self-evident from the graph. That's all. Just draw the graph and interpret it. You get your answer. Is that okay? This was the 12th one. I'm sorry. This is the 12th one. This is the 12th one. 13th yet to be explained. Yeah. Which one you have a problem with?
Sir, why isn't the D statement correct?
See, temperature increases very slowly. We're talking about that is the rate of increase, but it increases now. As long as it increases, it is delta U is present. Temperature increases slowly, you also grow very slowly. That doesn't mean you haven't grown. Like that. Yeah, is that okay?
Yes, sir.
13th, 15th one. 15th one, you just write the graph for it's a adiabatic process. See, PV power gamma is a constant. So we say log P plus gamma log V is equal to log constant. If you differentiate, no need to differentiate, we can say log P equals minus gamma log V plus log K. This is the graph you have drawn, y equals mx plus c. If you look at it, the slope is minus gamma. In the between the two lines, which has the greater slope? X has the greater slope. So we can say gamma x is greater than gamma y, which means 1 plus 2 by fx is greater than 1 plus 2 by fy. Or we can say fy is greater than fx. That's all. Other things are obvious. So f2 is greater than f1 and cv2 is greater than cv1. Both these are evident from here. Is that okay? See, we have to find out which one of this is it q1 or q2? Now, if you want to compare q1 or q2, q1 is nothing but w1 plus delta u, and this will be w2 plus delta u. Delta u is same for both of them, because 1 to 2 is same as 1 to 3 in terms of temperature difference. Okay, 2 and 3 are in the same temperature. So if you compare the work done, then you can say whosoever has the greater work done will also have the greater heat. Okay. Now, in order to compare it, I will have to find out the area under the graph. Area under the graph is this. What is W1? W1 is equal to half into, what is the area of a trapezium? Half into sum of the parallel sides into the height between them, which is V2 minus V1. Is that okay? Likewise, W2 will be half into sum of the parallel sides will be P1 plus P3 into V3 minus V1. Is that okay? Now, what we do is let us find W1 minus W2 is equal to half of, how many terms are there in the first one? First one terms are P1 V2 minus P1 V1 plus P2 V2 minus P2 V1 minus second one terms P1 V3 minus P1 V1 plus P3 V3 minus P3 V1. You have got these terms. Now P1 V1 cancels off with minus P1 V1. P2 V2 is same as P3 V3 because they are isothermal. So these two terms go away. Now let's calculate the things which are remaining. Half of, what do you get? If you combine these two terms, you get P1 into V2 minus V3 plus the next term is V1 P3 minus P2. This term. If you notice, both these terms are negative. P3 is less than P2 and V2 is less than V3, which means W1 minus W2 is less than 0, or W1 is less than W2, or Q1 is less than Q2. Well, that's the answer. Okay, so we're getting into the heat transfer chapter. So you are aware that there are three modes of heat transfer. What are they namely? That's right. So convection, it depends on situations and what is the air blowing, etc. There is no standard formula for it. It will depend from situation to situation, differ. So we are not dealing with that in our course. So that leaves us with conduction, radiation, and that's conduction is what we're going to start now. So we write down the first equation of heat current. Quantity of heat transferred per unit time, dq by dt, heat. Let us see what is it dependent on. Suppose I say that Suppose I say this is very hot. Now if this is very hot, now how do you examine? Now, normally suppose you have some water or oil bubbling there, then you will know it's very hot. Otherwise I say that you've got to touch it and find out. So will you touch like this or will you touch like this? You touch like, now what makes you do that? Why are you doing that? Why not this? Why don't you take an oath on that?
The surface area of touching.
So you are aware that the more the area, more will be the heat, less the area, less will be the heat. Even if it's damn hot and you get a little black spot on your finger, you know it's very hot. But you're okay with it, right? So we understand that here the heat current is proportional to the area. That's the first thing you realize. Then, now sometimes you might have a fever, and if you touch yourself like that and find out, now that's not a right way of finding out, because if you are 104 here, 104 here, you won't feel it. You ask somebody, your friend, to kind of touch it and say, just check whether I'm having fever. Say your friend touches you and say, hey, you are very hot. Now that's way to find fever, because your temperature is more and the friend's temperature is less, so there is immediate rush of heat. So a difference of temperature will cause the heat current to flow. So delta T is required. If there is no difference of temperature, no heat flow. And thirdly, you know that suppose in cooking, you always use a ladle to cook something. Now you know that the handle is there. The closer you go to the mouth of the handle, near the dish, it will be hotter. The farther away you go, it will be colder, isn't it? So what does it tell you about the length part in heat? Inversely proportional. That's right. So it's inversely proportional to the length of the medium. Now in physics, we normally have like that, so we put a proportionality constant here, we call it as K, and give it a nice name. This one is called as coefficient of thermal conductivity. Heat flows from hot to cold. Since it goes as temperature decreases, now this is just a modulus value of writing. You can also write it as H equals minus Ka dt by dx. We put a negative sign because this is called temperature gradient. What is the difference between rate and gradient? What is rate? What is gradient? Rate is with respect to time, and gradient with respect to distance. So here we have temperature gradient. The dt by dx is negative. As you go here, the temperature decreases. Since this is negative, to make it positive, we put on the negative. That's the heat current. This is the equation in calculus notation. Now let's see something else. When I am saying heat current, I am reminded of electric current. I equals delta V by R. That's the Ohm's law. When you have a potential difference, a current flows. And the current flow is given by delta V by R, the Ohm's law, like that. Now, even this one looks pretty similar. See, this one is also written as delta V by rho L by A. Have you seen this formula? Resistivity length per unit area. Now I can change resistivity. If I take a reciprocal, it becomes conductivity. So rather than write like this, can I write like this? L by sigma A. Sigma is conductivity. Now if you rearrange this, H equals delta T upon delta X by Ka. We can rewrite this like that, this equation. So this one looks exactly like this. You have electric current, heat current, temperature difference, potential difference, length area, thermal conductivity, electrical conductivity. So the analogy is perfect. So we call this also as resistance, albeit thermal resistance. Electric current or heat current, they are analogous. For that matter, all currents are. You have electric current, heat current, or for that matter, water current. Water flowing per unit time, the mass or volume. Why does a river flow and a lake does not? Or you might say what flows is called a river, that's another matter. But What is the reason? Why does the water in one flow and why does the water in the other doesn't flow?
There's no input and output to the lake.
High difference.
There's stable equilibrium.
Input output means any point you can consider as input as long. That's not an input output. Why does it flow?
Difference in the height.
Yes, it's a difference in height. A river is an inclined plane. It may not be evident in on the top, it might look flat, but it's a gradual inclination. A river always goes from the mountains to the seas. A river is a waterfall. We might not call it that. If there's an abrupt fall, you might call it a waterfall like a Niagara Fall. But any river is also a fall. What's the difference? No difference. The falling happens over gradually or it happens abruptly. There is a fall. So for a water current you require a height difference. For electric current you require a potential difference. For heat current you require a temperature difference. It's like that. So we are going to make some heat circuits. What have I said? Just like electric circuits, we can make heat circuits, and rather I'm going to use your background in electricity. I'm sure you know how to deal with series and parallel circuits. Yeah? So let's use that. Let's see. So take down these equations. We have the heat current equation and thermal resistance. Look at that. Let me say a little about this. Thermal conductivity. The thermal conductivity is the property of a material or a substance. You have materials which have good K and bad K. So suppose you compare two things, wood and metal. Which is good K, which is bad K? Metal is a good conductor of heat and wood is a bad conductor of heat. That's why you have wooden handles on certain things which are going to be hot. And likewise, ice itself. Ice is a bad conductor of heat. Eskimos make igloo, and inside the igloo it is pretty warm because the ice walls prevent the heat from going outside easily. And likewise static air. Why do you wear a sweater? Why do you wear a jacket? Wool and cotton. Which one makes you, which is hot? Which has a better K? Yeah, it has nothing to do with the wool and the cotton. The woolen fibers, if they trap air. They trap air and the air is the bad conductor of heat. That's why in air-conditioned compartments in trains and planes, you have double-walled windows. Between the windows you can catch static air as an air sandwich there. Now that prevents the heat from going out. So that's also giving you a bad K. Okay? So K, so we have an idea of what is K like. So K depends on the material, of course. So let's look at it. I'm going to give you a question now. We have a glass slab, not a glass slab, two slabs, K1, K2, of length L1 and L2. The temperature here is T1, temperature there is T2. Let's assume T1 to be greater than T2. Now what will happen is, heat will go from the higher temperature to lower temperature like that, but there's the heat going there. Now heat can also go from the sides like this. It can radiate out, etc. Unlike electric current, which you have a wire, means it will only go along the wire. It won't go sideways. But heat can escape from the sides. So what we do is we thermally insulate this to make the analogy exact. Now this process is called it is called lagged. The thermal conductor has been lagged, which means it's been suitably insulated. I'm saying it for the first time. Rest of the times it will be assumed. I won't repeat this idea again and again. In all our questions, it is thermally insulated from the sides so that heat doesn't leak from the sides. It will go only along the length. So heat is going like that. So what is the question? The question is, what is the temperature at the interface? This is the question. So the way we deal it is, we think of this as one resistance and this is the other resistance. The potential temperature is T2. The temperature here is T1. The temperature here is T. This is called R1. This is called R2. Now you know the heat current which is going is H. I have drawn an electrical equivalent of that circuit. So the heat current which passes through the first one we can write like this: temperature difference T1 minus T upon R1. The second one I can write T minus T2 upon R2. So we have to solve for T. Well, before that we'll have to get R1, R2. What is R1? Delta X by Ka. In this case it will be L1 upon K1A. In this case it will be L2 upon K2A. So just cross multiply, let me know what is T. That's your answer. T equals?
So T1 L2 plus T2 L1 by L1 plus L2.
Yeah, can you say it again? T1?
T1 L2 plus T2 L1 upon L1.
No, what happened to K? T1, L2, K2 must be there. You will get something plus something and something plus something like that. But what is that? I think you get 3 terms here on top. K1, T1, L2 plus K2, T2, L1 upon